My dear student, you are most welcome to my class. Myself Dr. Aqliuddin Ahmed. My dear student, today I am going to introduce a new lecture series on group theory. Okay, so in this lecture series I will try to cover the syllabus on group theory, and basically this lecture series will be helpful for the students who are pursuing BSc in mathematics as well as MSc in mathematics. And this lecture series also I will try to discuss some important portions, some shortcut trick which will be helpful for those students which are preparing for CUT or GATE exam. Okay, this is the first lecture. So in this lecture I will try to cover or discuss some basic concept on group theory, some basic structure I will discuss today. Okay, in the first I will try to discuss about the binary operation. I think all of you know the operation, right? Like addition, subtraction, division, all those things already you know, right? These are the operations simply, right? But here we need here binary operation. Now what is binary operation, guys? Just 1 minute, I will change the color. Okay, now what is binary operation, guys? You see the formal definition of binary operation first. You see here, a binary operation is star on a set A is a function star from a Cartesian product A to A, and it is denoted like this way or this way. You see here, they consider a mapping from what? From the set A Cartesian product A to A, and they consider that mapping is phi star. Okay, now this star is called here binary operation. Now you see here, if we consider a set is nothing, suppose A comma B, this is the set. Okay, so what will be a Cartesian product A? Yes, I think all of you know what will be the a Cartesian product A. This will contain a comma A, right? A comma A as well as a comma B and as B comma A and B comma B. These are the elements on this set. Okay, and here we consider A and B. Now you see this star is map this element to this set. That means this star operates, suppose these two elements, and this star give this element. Okay, that means the image of this element under this operation is this one. And you see, this star is nothing, star is a mapping from a Cartesian product to A. That means this element is nothing again in A. And also you remember here A and B both are the elements of A. That means what we see here, star is a binary operation, means here any two element if we consider from the set A, and this star operate that elements and make a new element that is also in again in A, right? That means what we can say, this set A is closed with respect to this star, right? So simply what we can say now, this star we can say a binary operation only when this set A is nothing closed with respect to this binary operation. So the definition of this binary operation we can define like this way also. Then an operation is said to be a binary operation, one is said, suppose capital A, only when this A is closed with respect to that operation, right? So simply this way we can define the binary operation. Now I will consider some numeric set we consider, and particular operation I will consider, and we'll try to verify whether that operation is a binary operation or not. Okay, suppose if we consider the set is nothing, this is natural number, set of natural number we consider, and suppose we consider the operation is our addition, right? This is nothing, this is our star we consider. Okay, now you check whether this star this plus is binary operation on this set N or not, right? So you see this set 1 means N means here this will contain this 1 2 3 4 5, these are all the natural number this will contain, right? Now you take any two elements from here, suppose 4 and 5, and operate them. This is our operation, right? So what we'll get here, 9. Now you see this 9 is also in here. If we consider any element from this set of natural number, and if we operate by using this operation, you will get always a natural number, right? That means this plus is a binary operation, right? Yes. Why this is binary operation? Because this set of natural number is closed with respect to this addition. Because if you take any two elements from here and if you use this operation and operate them, then we'll get a numbers that will be always a natural number and that will be here, right? So this plus is a binary operation. Okay, now what about subtraction? Suppose if you consider this operation, this is our star. Now is this operation is a binary operation? Yes, you check here. Suppose 4 minus of 5, what will be this one? This will be minus 1. Now the question is that whether this minus 1 is here or not. No, because this is contain only the natural number and minus 1 is the not natural number. That means what we see here, this set of natural number is not closed with respect to this subtraction. That means this subtraction is not a binary operation, right? Is it okay? Similarly, if you consider suppose set of integer, right? Then you consider the operation is subtraction, suppose. Then what we get to see here, is this or binary operation, whether set of integer is a closed with respect to subtraction or not. You see here, this set of integer contain this set of integers. Suppose this is our set of integers, so it will contain 1 0 1 2 3 and so on, minus 1 minus 2 minus 3, all the values will contain. Okay, now you consider any two number from here, suppose 1 and 5, right? And you take minus operation, what will be this one? This will be minus 5. Now whether this minus 5 is here? Yes, right? Suppose 2 1, so 2 minus 1, this is 1, again 1, so again also in here. So what we see here, this set of integer is nothing, this is closed with respect to subtraction also. That means this subtraction or this minus operation is a binary operation, one we set in one set of integer, but this is not the binary operation on we set on the set of natural number. Is it okay, I think? Okay. So now you see, here we consider this binary operation. Here we consider suppose G is a non-empty set and together with a binary operation. What we consider here? We consider a non-empty set G and together with a binary operation, right? Now this structure, right? This structure, that means this non-empty set together with this binary operation. This structure, this together we call here group wide, or you can say here binary algebra, or sometimes we call here quasi group. Is it okay? So what is quasi group or what is group wide? This is nothing, is set, non-empty set together with a binary operation on that set, right? Then that structure we call here a group wide, right? Similar, you see here n plus, this is a group wide, z minus, this is a group wide, but n minus, is it group wide? Is it group wide? No, this is not group wide because this is not a binary operation on n, right? This is not group wide, but this two will be group wide, this will be group wide, right? Here suppose z and multiple, this also will be group wide, but z and division, right? You just verify whether this division is a binary operation on z. No, this will not be. This is not a what? This is not a group wide. Is it okay? So we can easily verify this type of structure, whether that structure is a group wide or not. Is it okay? Okay, now you come to the another structure, and with structure which is also important. Here you see this is called here semi group. Now what is semi group? Similarly, again here we consider any non-empty set, suppose group, together an operation, right? And of course this operation is nothing, this is binary operation, don't confuse, binary operation. Okay, a non-empty set together with a binary operation. This structure is called here semi group if what happen, if it satisfies the associative property. Okay, if it is satisfy the associative property, that means what we see, the group together with a operation satisfy these two conditions. What are that condition? One is closed or closer, right? Closure means why this is necessary? Because we need here binary operation, and this will be binary operation only when G is closed. So the first condition will be closure or closed property. Okay, the second one we need here associative, right? Associativity. So associativity also we need. So if a non-empty set and an operation satisfy these two conditions, we call that is a semigroup. So you just come to the definition of semigroup. Here you see an algebraic structure, that means G and star, is called a semigroup if the binary operation satisfy the associative property, this property. Right, you see they mention here the binary operation, and binary operation, this concept or this condition will give this one, close or closure property. And the second one also we need here associative property. Now what is associative property, guys? What is associative property? You see this is the associative property. You see here associative property means we consider here any three elements, suppose A, B, C from the set G. Okay, and if we operate like this way, A, B, star, C, and if we operate first these two and then this one, okay, if this is equal to A star of B star of C, that means what we see here, we just operate this one first, after that this one. Okay, if these two are equal, then we call this group satisfy the associative property. Actually this is the associative property. Okay, now we consider here some numerical questions, some numerical problem. Suppose if we consider this set of natural number and the operation is plus. Now the question is that whether this n is closed with respect to addition. Yes, already we verified, right? And also you can say whether this plus is a binary operation or not. Yes, this is a binary operation, because if we consider any two elements from n and if we add them, again we will get a natural number. Okay, that means this natural number is closed. That means the first condition will satisfy here. Now for the second one, that means for associativity. So we consider any three values from here, suppose 1, 5 and 7. Okay, these three values we consider. This is from the set n. Okay, we consider these three values. Now you just find these values. So first you operate these two one and then this one. What we get here, you see 1 plus 5 means 6, 6 plus 7. What will get here? This will give 13. Okay, similarly you just try to find this value. But in this case we do first we operate this one. Okay, first we find this in. What will be this value? 1 plus 5 plus 7 means 12. So 12 plus 1 means 13. Here you see we get 13. Here also we get 13. That means these two are equal or not? These two are equal. Similarly, if we choose any three elements from this set n, and we can easily verify this property. This property always will satisfy. That means the set of natural number is satisfy the associative property with respect to addition. That means the set of natural number is nothing. This is a semigroup. This structure is a semigroup, right? But here set of integer and minus. Okay, this operation. But you see here, this subtraction is closed or is a binary operation or not? Yes, this set of integer is closed with respect to the subtraction. Yes, that means this closure or the first condition is satisfied here, right? First condition is satisfied. Now what about the second condition? You see, you consider any three elements, suppose from here 1, minus 2 and 5. This is from the Z. Any three elements we consider, right? Now you try to operate them. Okay, 1 minus of minus 2 minus of 5. Okay, you just operate first one and then this one. Okay, and here I will try to find here 1 minus of minus 2 minus of 5. So you first find this one and then this one. Is it okay? You just remember minus 2 is an element from Z. Okay, so first one and then last one, first and last one. Okay, now we try to simplify this one. What we get? 1, this minus minus will be plus, so 1 plus 3 sorry, 1 plus 2 means 3. So 3 minus of 5, this will be minus of 2. That means these values we get here minus 2. And similarly, you just try to simplify. What will be this one? 1. This minus 2 and minus 5, this will be minus 7. So this is minus of minus 7. Now you see this minus minus will be plus. So 1 plus 7. So this is final, will get 8. Now whether they are equal? No. You see, that means with respect to this subtraction, the set of integer is not satisfy the associative property. That means this is not the semi-ring, right? So this type of structure will be there. Just you need to verify whether that structure is from a semi-group or not, or whether this structure is from a groupoid or not. I think you can easily verify now, right? So now you try to verify for this one, R plus, okay, Q sub multiplication, okay, Z division, okay, this type of structure you try to verify yourself, okay, just you try to verify yourself whether this structure is from semi-group or not, right? So I think this is very easy. One is n plus, this is a semi-group. Z plus will be, Z multiple will be, Q multiple will be semi-group, but Z minus, this is not a semi-group, right? And one more important example is there. Here you see, this is the structure PS and union. What is PS? PS nothing, this is the power set on S, power set of S, okay, and the operation is our here union. And similarly, power set and operation is intersection. These two also form here semi-group, right? These two also have, try to verify this one. Okay, here you see, as we consider any small set, suppose we consider A and B, right? So what will be PS, guys? What will be PS? It will contain all the subset of this set S, right? So the first subset is phi, another subset will be this one A, another will be B, right? Another will be A and B. So these are the subset. That means this PS is a set which contains these elements, right? These four elements. This is set, this is an element, this is an element. So these are the element of this P set, right? Okay. Now we consider here operation is what? Union. So this is our star. Now this is our star. Now first thing we need to verify whether this PSU is semi-group or not. That means we need to verify here this PS is close with respect to this union, or is this satisfy the associative property or not, right? So for closure, what we do here, just you consider any two elements here, from any two, suppose phi union any element you consider. Okay, if we operate this one, what we get? Phi and union A will be this one. So again this is here. Okay, again you see any element if you consider A union B. So what will be this one? This will be A and B. So if we operate these two elements, again we get an element which is also here, you see here. Similarly, if we consider this one, suppose B union AB, right? So this will be AB again, AB again. So again this is also in PS. So similarly for any other elements, you can easily verify this operation, operate them and make an element that will be also here. Right? That means this PS is closed. So first condition is satisfied. Right? First condition is satisfied. Now second one, what we need? We need to prove for associativity. Right? Associativity. So for associativity, what we do here? We consider any three elements from here and we check whether that is satisfy the associative property or not. So first we consider this element. This is first element. Okay, sorry. This is our second element, right? And this is our third element. Any element you can choose from here. And this is our operation, right? This is our operation. So first we operate this one, these two, and then this one. You check what will be this value. You see what will be this value? A and B. That means here this will be AB, right? Union of AB. So if we take union, what we get? AB will be that. Okay, this value we get AB. Again, you just try to find this another value, A union B union AB, right? AB. Now you first operate these two one and then this one. Okay, so AB is here, A is here, union. Now what will be the union of this one? This will be AB only. right? I think all of you are familiar with union of any two sets, right? Okay, now what will be this value? This will be AB, right? The union of this one will be again AB. So now you see here AB, here also we get AB, right? That means the associative property is satisfied here, right? For any other elements, if we consider one element is phi, any two elements if we consider, similarly we can easily verify this associative property, right? That means what we see, the set of all subset, that means the power set with respect to this union form a semi-group, right? Similarly you can easily verify for intersection also, right? So you try to verify yourself this whether this is satisfy the semi-group or not. I think this will satisfy the all the properties of semi-group, right? So you just verify yourself. Okay, so now come to another important structure which is called here monoid. Now what is monoid, guys? Monoid is nothing, this is a semi-group. A semi-group is called a monoid if there exists an identity element E in G such that this is happen, right? That means a monoid which has the identity element with respect to that operation, right? Now first they call here semi-group. Semi-group means it will be closed, it will associate, right, these two satisfy, and then it has identity element. So identity element also exists. So existence, you can say existence of identity element, right? If these three conditions satisfy, then this structure, suppose here G and with respect to this binary operation, this structure is called here monoid, right? So this is the formal definition, but actually if we want to verify whether a given set and a binary operation is a monoid or not, actually we need to verify whether these three conditions is satisfied or not, right? So now what is identity element? Right, now you see what kind of element is called identity element. You just try to recall the previous concept here. You see, I think I have discussed identity element in the previous lectures. Okay, you see here, suppose if we consider the operation, there is an element 1, and if you operate any element with this 1, suppose 2, we'll get the same element. Here you see 1 into suppose 5, what we get? Always will get 5. That means 1 is an element, one element. With this element, if you operate any other element with respect to this multiplication, we will get always that element. Here you see, right? So in this case, this 1 is called the identity element, right? Identity element, but in which operation? With respect to this multiplication, right? Again you see, if we consider the operation is suppose addition, what we consider? The operation is addition. Now you see there is an element, suppose G. Now if we use this operation addition with this 0, you always get that element. Here you see 0 plus 5, always will get 5, same element, right? That means 0 is an element. If we operate this addition and with if we operate any other element, right, by using this operation addition, we'll get that element always, right? That means this 0 is here identity element, right? So you just remember in case of addition, 0 is identity element. In case of multiplication, 1 is the identity element, right? So sometimes 1 is called the multiplicative identity, 0 is called here the additive identity. So you must remember this thing, right? So finally the identity element means here, if we consider any star, operation is star, an element suppose E, and if we operate any other element with this E, if we get the same element, right? Or same thing also we can write like this way also, if we get same element, right, for any element of E, for any element, if we get, then this E is called the identity element, right? So you see here, now if we consider the set is nothing, suppose set of natural number. Now you say whether the set of natural number exists the multiplicative identity, that means it contains the multiplicative identity. Yes, क्योंकि इसमें कितना है 1 है, so 1 is present here, that means the multiplicative identities exist here. But whether the additive identity, that means 0 is exist here, you see the set of natural number contain 1 2 3 4 and so on. 0 does not exist here, right? That means the set of natural number does not exist the additive identity, but multiplicative identities exist here, right? But in case of suppose set of integer means 0 plus minus 1 plus minus 2, okay, this one. So this is the set of integer. Now whether this set of integer contain the additive identity, yes, 0 is here, it's contained. Again you see the multiplicative identities exist, yes, 1 is also here. So the set of integer contain or exist the additive identity as well as multiplicative identity. Is it okay? So here you see, now just I will try to consider some special structure and we'll try to verify whether that structure is from a monoid or not. Okay, which one will consider? Okay, suppose if we consider this first one, suppose multiplication, set of natural number and with respect to multiplication. Now whether this satisfy all the properties of monoid, yes, you see here, first thing it will be closed. Why this will be closed? Because you see, if we consider any two natural number and if we operate them, you must remember the operation is multiplication. That means if we multiply them, what we get? You will again get a natural number or not? Okay, always will get a natural number. That means this is closed. Again it will satisfy the associative property, right? We can easily verify the associative property. And the last one, whether it exists the identity? Yes, because 1 is there. Because in case of addition, multiplication, 1 is the identity, so it is also here. That means this will form a monoid. But in case of n plus, whether this is a monoid? No. This n will satisfy the closure property, it's okay. It will satisfy the associative property, it's also okay. But there does not exist the identity because 0 is not here. 0 is not this set, right? So this is not the monoid. This structure is not the monoid, right? Although this is semi-group, right? This is semi-group, but this is not the monoid. Similarly, we can easily verify for this one also, Z suppose plus. So whether this is a monoid? Yes, this is a monoid because you see set of integer is closed. Already we have verified. This is associative also, already we have done. But it has existence of identity or not? It exists identity. Because 0 is here or not? Additive identity is 0. 0 is also here. So this is nothing, this is the monoid, right? Similarly, if we consider this one, Z multiple, whether this is a monoid or not? Yes, this is monoid because this will close with respect to multiplication. This will satisfy the associative property and it has identity element. Identity element with respect to multiplication is none and 1 is here. Right, so this will be monoid also. Is it okay? So same way we can visually verify for this R plus, right, or R minus, right, or even for this set PSU, whether this is a monoid or not. Yes, I think this will also satisfy the monoid property, right? So you just verify yourself. PS and intersection, right? This also will satisfy the all the properties for monoid. So this also will be a monoid, right? So you see here some examples we consider here. NS, this is a monoid. N plus, this is not a monoid because identity is not there, right? Here you see PSU, PS intersection, this will be the monoid, right? Okay, you see the another group, another structure which is called group. Here you see, you must remember this structure is most important because in your title here you see group theory. We are discussing about group theory. That means this group structure is more important, right? So now we try to explain here the group structure. Now what is group, guys? Similarly, here also we consider a non-empty set, suppose star a Z, and together with an operation, right? If this structure satisfies here 4 properties. One is closure properties. Here you see the first one is closure property. Second one is the associative property. Third one, there will be another 2 properties. Third one is nothing, this is called the existence of identity, and the fourth one is called here existence of inverse. So I will discuss one by one. I think all of you know about the closure property, already we have discussed. That means for if you consider any 2 elements from the set and the operation, if operate them, you will get a new element, and if this element also in this set, then we call this is closure, right? This is closed. Okay, this is, and also we know this associative property also we have discussed, existence of identity also we discussed. But what about the existence of inverse? That means if for each element in this Z has inverse, right? So now what is inverse? You see here, suppose if we consider the operation is suppose multiplication, right? And you just try to remember the multiplicative identity is 1 here, right? So what happens, you see, suppose we want to find the inverse of 2 with respect to this multiplication, then you just search a number such that their multiplication is equal to the identity. Here you see 1 upon 2 will be there, because 2 and 1 upon 2, if we multiply them, then we will get 1, right? Similarly, if we want to find the inverse of 5, then this will be 1 upon 5, because their product is equal to 1, right? That means here you see the inverse of half will be 2, the inverse of 2 will be 1, no, half, right? Similarly, inverse of 5 is 1 upon 5, right? So these are nothing, this way we can easily find the inverse of any element with respect to multiplication. But similarly, we can easily we can easily find the inverse with respect to addition also. Suppose the operation is addition, okay, and suppose we want to find the inverse of 2. Now you must remember what is the identity element with respect to addition. This is 0. Now you search on numbers such that their sum is equal to that identity. Here the minus 2 will be that number, and if you take sum of them, you will get 0 here, right? So minus 2 is the inverse of 2 with respect to addition. Similarly, suppose here you see, suppose minus 5, we want to find the inverse of minus 5, then what will be that inverse? If you just search one number, and that will be 5 here, if we add them, you will get 0. That means the inverse of minus 5 is 5, right? This way we can easily find the inverse. Here you see the inverse of 2 is here half, but here inverse of 2 is minus 2. That means the inverse property or inverse will depend upon the operation, right? For different operator, maybe their inverse also different, right? Okay, so inverse of what we means here? So a number, suppose A, and suppose we want to find the inverse of this number, then what happens? That inverse will be another number, suppose B, and if we operate them, we must get here identity element, right? Then this B is here the inverse of A, right? And generally the inverse of A we write like this way, we denote like this way, right? That means A star of A inverse, what will be this one? This will be the identity. So this is the inverse of A, right? Now according to these 4 properties, here you see, if we consider and multiplication we consider. Now just try to verify whether this structure is a group or not. Okay, you see we need to verify 4 properties, right? One is closure, another is SO, and then what? Identity, right? Identity and inverse, right? These 4 properties we need to verify. Okay, first of all, for closure, yes, this satisfy the closure property, already have done. This is satisfy the associative property. This has the identity element with respect to multiplication because 1 is there. Now whether this inverse exists or not, here you see this set contain 1, 2, 3, 4, 5 and so on, right? Now suppose the inverse of 2, what will be the inverse of 2 here? 1 upon 2, right? Inverse. Inverse of 2 is 1 upon 2, but whether 1 upon 2 is here? No. That means the inverse of 2 is not here. Similarly, inverse of 4, what will be the inverse of 4? That will be 1 upon 4. 1 upon 4 is also is not there. That means what we see, this set of natural number is not exist the inverse element, right? With respect to this multiplication. That means this is not a group. This is not a group. Is it okay? This is not a group. But here you see, if we consider this set, suppose if we consider which set, okay, suppose set of integer and operation is plus. Now we check whether this is satisfy the group properties or not, all the properties or not. Okay, you see the first one, yes, closure property always satisfy. This is associativity, it has identity because 0 is also there, right? This is the set, you must remember this one. Here minus 1, minus 2, minus 3, this is the set, right? So first 3 properties is enough. Okay, this is okay. Now for the last one, for inverse. What is the inverse of 2? That is minus 2. Here you see the minus 2 is also here. So inverse of 2 is present. Again, suppose if we want to find the inverse of minus 3, what will be the inverse of minus 3? Here you see we need here 3, then only we get 0. That means the inverse of minus 3 is 3. 3 is also there. Is it okay? So we can easily find the inverse of each of these elements of this group, right? So that means this set of integer and this plus operation together give here the group structure, right? So the set of integer form a group with respect to addition, right? So similarly you can easily verify for r plus, right? R plus also will be group. You can easily verify. Now r multiplication, whether this is a group or not, you just verify yourself, right? Q plus, whether this is a group or not, just you try to verify this thing, right? Your homework, right? You just try to verify this, all those properties. So finally, there are 4 properties, right? One is closure, another is associativity, another is existence of identity, right? Then another existence of inverse. These properties are there, right? Most of the structure is related to these properties. So if an structure satisfies the first property, then what we call, that is called groupoid, right? Or quasi group, sometimes we call quasi group. Is it okay? And then if an structure satisfies these 2 properties, that means closure as well as associative, if satisfy both properties, then we call it is semi group. Structure satisfy these 3 properties, if an structure satisfy these 3 properties, then that we call here monoid, right? And the fourth one and the last one, if they satisfy all the properties, all the 4 properties, then that is called here group. That is called here group, right? So you see, a group structure will satisfy monoid properties. It will be a semi group as well as groupoid. But here you see, monoid, a monoid will satisfy these 2 properties also. That means it will be semi group as well as groupoid, right? So okay, I think this is enough for today. Kindly share this link to your friends, and of course don't forget to subscribe to my channel. Okay, bye bye.